Hello, welcome to Rocky Biochem series. In today's video, I will explain to you how we perform some calculations on material or mass balance. Please, if you've not subscribed to my channel yet, kindly do so for me. I will be uploading a lot of videos on this very topic as well as other videos on biochemistry topics and molecular biology. Thank you very much. So mass balance, also known as material balance, is based on the law of conservation of mass. And this law makes us understand that mass can neither be created nor destroyed. In industrial settings like sugar producing or tomato paste producing industries, mass balance is applied there. So it follows this particular order. There is no way that whatever raw material, the mass of raw material that you are working with, you will end up having a product that is more than the raw material that you started with. That is why we say that mass is conserved when it comes to industrial settings and then other chemical reactions. Mass is conserved. The amount of substance entering the systems should always be equal to the amount of substance that is exiting the system. So to make calculations on mass balance look easier, always draw a diagram to represent the informations that are given to you. So let's consider this. If this is our evaporator, this particular topic we are going to focus more on how the evaporator is used to extract water from our raw material and then give us a product with a decreased amount of water, or let's say no amount of water in such a product. So to understand it better, always draw a diagram to represent whatever information given to you. So assuming that the diagram here represents our evaporator, the mass in, that is the amount of substance entering the evaporator system, should be always equal to the mass out, that is our substances coming out of the evaporator. So the substances that are coming out of the evaporator can be a normal product, or can be water, or it can be a waste substance. So they comprises of the mass out. So anytime you sum up whatever is coming out of the evaporator and then equate it to whatever was entering the system, that is the raw material, they should always be equal. So everything follows this particular golden rule. Mass in is always equal to mass out. Mass in is always equal to mass out. This is the golden rule that you should never forget when it comes to working on mass balance or material balance. So we should take note that whatever mass entering the system should be equal to whatever is coming out of the system. As I said already, under no circumstance the product should be greater than the mass, or let's say should be greater than the raw material, or let's say your raw material entering the system is going to be more than your product, or whatever is exiting the system. When such a situation happens, it means that there is something wrong with the evaporator system. Maybe there is impurities that have been added to the final product, and that is going to make it be more than your raw material, or the evaporator is consuming some of your product, thereby leading to loss. So when such things happen, that means the evaporator system needs to be checked. So let's make things clearer by dividing the calculations on mass balance into some various divisions. So we have total balance and then component balance. For things to be easier, always understand what total balance is and then component balance. I'm going to explain each of them to you. So for total balance, when we talk about total balance, we are focusing on this particular balance is going to focus on whatever is entering the system and then whatever leaving the system. So as I said from the rule given, mass in is equal to our mass out. So if the mass in is our feed, that is the raw material, it should be equal to the mass out. So the mass out here can be our product, that is, or let's say the amount of water removed, or our waste substance, etc. They all form the mass out. So these substances here should always be equal to our raw material. That is what total balance means. Total balance focuses on whatever, that is the total amount of substances entering the system, and then equate it to whatever is exiting the system. So in order not to forget, always remember that arrows pointing inside are always equal to arrows coming outside. Arrows pointing inward is equal to arrow pointing outward. So if only one arrow is even pointing towards the evaporator, as we can see here, it should always be equal to the total number of arrows that are pointing outside. So if we are to write total balance for this particular system, it is going to be our feed F to be equal to W plus P. F is equal to W plus P. So this represents total balance equation. That is, arrows pointing inside is equal to arrows pointing outside. That is how things are going to be. So now that we've gotten to understand total balance to be equal to whatever, that is sum total of whatever entering the system being equal to sum total of whatever are exiting the system, then let's understand what component balance is. Component balance is like focusing on one particular component found in the raw material. So in situation like, let's say we want to extract a pure sugar from a sugarcane, the sugarcane is going to be our raw material. So when we dive into the sugarcane, or let's say when we take sugarcane for instance, the sugarcane is made up of water and then the sugar. It is made up of water and then the sugar. So if we feed in sugarcane into this particular evaporator system, then we can perform component balance on the exact amount of sugar that is entering the system, and then equate it to the amount of sugar that is exiting the system. We are focusing on only the sugar alone, but we are not focusing on the water. And mostly they are given in percentage wise. Yes, so if you want to perform component balance, we obtain this by multiplying the percentage given for that particular component by the total amount of substance that we are given. So let's say in the case of the feed, let's say we have a feed that is entering the system, and this feed, the percentage of salt given was 10%. Multiply this 10% with the feed given. So we were not having the exact value for the feed, so we will just use F to represent our feed and then multiply it by the percentage of the salt present in it. So we should take note of that we don't just multiply the percentage given directly, we express it in a form of decimal. So in this case, the 10% will be expressed as 0.1. So you then come to the water. We take it this way, that since we are performing the component balance on the salt, we don't expect the water to contain any salt. So the percentage of salt contained in the water is taken to be 0. Then let's say the product contains 30% salt. So if you want to perform a component balance on the product, it is just a matter of multiplying this percentage, that is 30%, by the amount of product that is exiting the system. So in this case, we are not going to write 30, but rather we will write 0.3 because the percentage has to exist in a decimal form. So let's consider this worked example to see whether we have understand whatever we spoken about this time around. So the example goes this way. In production of sodium chloride, that is salt, from salt solution, 100 kg per second of feed solution containing 20% by weight sodium chloride enter the evaporator. The evaporator remove water from it to form a product containing 50% by weight salt. What is the amount of water removed and the product formed? Let me take the question again. In the production of sodium chloride, that is salt from salt solution, 100 kg per second of feed solution containing 20% by weight sodium chloride enter the evaporator. The evaporator remove water from it to form a product containing 50% by weight salt. What is the amount of water removed and the product formed? So this is the question given to us. So we are going to solve it step by step. So now this is the solution. Step 1. Draw a diagram to represent the information. The question is very long, but by drawing diagram, it simplifies everything. So, from the question, the amount of sodium chloride, that is the salt entering the evaporator, was given to be 100 kg per second. That's the flow rate of the salt solution. So, We also had the percentage of the salt contained in this solution to be 20%. So in this case, we will write it in decimal form, that is 0.2. And then the question also said that the evaporator removed water from it. So that is why there is this W here denoting that we removed water from the raw material, that is the sugar solution. And then the product also exited the system with a percentage of salt contained in it to be 50%. So we will express this percentage in the form of decimal. After using a diagram to explain the question, the next thing is to solve the question itself. By drawing the diagram, you have solved about 80% of the question already. So the first thing that you have to do, after drawing the diagram, is to write a total balance equation. We have to write total balance equation for the question based on the diagram that you have drawn. So from the diagram, we can go by this. Our F is equal to W plus P. That is mass in is equal to mass out. We are following the general rule about mass balance. Whatever is entering is equal to whatever is exiting. So in order not to forget anything, just take note that arrows pointing inside is equal to arrows pointing outside. Arrows pointing inside are equal to arrows pointing outside. So in this case, it was only F that is pointing inside, and then the W and then the P are arrows pointing outside. So they will be found at one side of the equal sign, and then the F, which is only pointing towards the evaporator, will also found on the other side of the equation. So we were having the flow rate of F to be 100 kg per second. So we are going to have 100 to be equal to W plus P. And this becomes our equation 1. So now that we've gotten an equation for the total balance, we can then continue. Let's write an equation for the component balance. The first equation is for the total balance. Then we have to write an equation for the component balance. As I kept saying this. The component balance actually focus on a particular component. So let's say it focus on salt in this case, or it focus on water. So in order for things to be easier, we go by focusing on the salt as the component of interest. So we can see from the question that the feed solution, that is the salt solution, was having 20% of it being salt. So if you want to perform component balance, that is amount of salt entering the system to be equal to the amount of salt leaving the system. That is all that it means. When you are performing component balance on a given component, amount of that component entering is equal to amount of that component what exiting. So the amount of salt entering is equal to the amount of salt exiting the system. So if you want to know the actual amount of salt entering the system, it is just a matter of multiplying the percentage given for the salt, that is the 20%, by the total feed available there. So the 0.2 will multiply the F, and it will be on one side of the equation, since it is the only component that is pointing towards the evaporator. And then the W will multiply the amount of what? Amount of the salt that is found in it. We take the water to be what? To be pure, and hence there is no salt present in it. So the percentage of salt present in the water will be 0. That is why the W is multiplying 0 here. And then the question was also saying that there is 50% by weight of salt present in the product. So in this case, we will multiply the product, that is the P, by 0.5. So we are expressing the percentages in a form of decimal. That is how the equation will be. So we will then put in 100. That is, the question was saying that F is equal to 100. So 100 multiplying the 0.2 is going to be W multiplying 0 plus P multiplying 0.5. So we are going to get 20 to be equal to 0.5 P, and hence we will have our P to be equal to 40 kilogram per second. So after getting our 40 kilogram per second to be equal to P, then we can boldly substitute this value into our equation 1, and then obtain our W to be equal to the 60 kilogram per second. So this question seems so easy. It is so easy to understand. But there are some situations whereby some questions are a bit technical, and then they even require the use of 2 different evaporators. So let's consider this particular reaction and then understand how we go by such questions. So in a process for the production of sugar from cane sugar 4,000 kilogram per hour of solution containing 10% by weight sugar is evaporated in the first evaporator, given at 18% by weight sugar solution. What is okay? This is then fed into a second evaporator, which gives a product of 50% by weight sugar. Calculate the water removed from each evaporator, the feed to the second evaporator, and then the amount of the product, assuming steady state. Let me take the question again. In a process for the production of sugar from cane sugar, 4,000 kg per hour of a solution containing 10% by weight sugar is evaporated in the first evaporator, giving at 18% by weight sugar solution. This is then fed to a second evaporator, which gives a product of 50% by weight sugar. Calculate the water removed from each evaporator, the feed to the second evaporator, and then the amount of the product formed, assuming steady state. So this question seems so technical. You can decide to pause this video and then try solving it, but let's keep on solving this question together. So for the solution, as I keep on saying, we solve these questions step by step. So our first step is to draw a diagram to represent the information. The question is very long, but we shouldn't be panicking. We should just break things down and then draw the necessary equation or draw the necessary diagram to represent whatever information given to us. So this is how the system will look like. We are going to use two evaporators. It's like the first evaporator couldn't remove enough water from the raw material, that is the cane sugar. So the product exiting the first evaporator was serving as a substrate, or like serving as a raw material for the second evaporator. So it then entered the second evaporator, and then we remove water from it to form our final product. So this is how it is going to be. So this is our raw material, or let's say this is our feed, and this feed is entering the evaporator 1, and then water is going to be removed from it to form solution product A, and then product A will serve as the raw material for evaporator 2, and then evaporator 2 will remove water from it and then give us our final product. So the question was also saying that the amount of sugar or present in the cane sugar is what, 0.1, that is 10%, and then the amount that exited the first evaporator was also 80%, which is 0.18, and then the amount present in the final product was also given to be 50%. So that is why it is written as 0.5. So after getting your equation, your diagram right, you have to move on and then write your first equation. That is the equation for the total balance. So the total balance is going to be F to be equal to W1 plus W2 plus P. You might be asking yourself that why is it that we have omitted the A? Don't forget that the two systems, that is evaporator 1 and then evaporator 2, are considered to be a one bigger system. So whatever entering this bigger system should be equal to whatever exiting this bigger system. So it is only F that is entering the evaporator system, and then the products, or let's say whatever it is exiting the system now, is going to be our water from the evaporator 1 and the water from the evaporator 2, as well as this particular product. So we are going to substitute these figures in there. We have the flow rate of the feed to be 4,000. So you will bring in the 4,000 here, and then it is going to be equal to W1 plus W2 plus P. So this becomes our equation 1. And then we will perform component balance on sugar for the entire system. Component balance on sugar for the entire system. So as I said, component balance is obtained by multiplying the percentage given for that component by the actual amount that is entering, or let's say exiting the system. So we will multiply our feed by 0.1, which is the percentage of the sugar present in the cane sugar, and then equate it to W1 multiplying 0. The W1 is multiplying 0 because the amount of sugar that we are expecting to exit or through the water portion is assumed to be 0, because the water should be pure and it should be devoid of anything like this particular sugar. And then the W2 portion here is also saying that water is removed, and then for this particular water too, we are not going to expect anything like sugar present in it. And then the last thing is going to be the percentage given for the sugar, or was given to the sugar was 0.5, and then we multiply this by the product, that is 0.5 multiplying the p. So when we fix in the figures in there, we are going to get 400 to be equal to 0.5 p, and then by solving it, we are going to get our p to be equal to 800 kilogram per hour as the flow rate. Please don't be confused, okay? After getting your total balance equation, we have to write equation for component balance, and component balance is equation is written with respect to a particular component. So in this situation, we are considering the sugar. We are considering the sugar as our component. So the percentage given for the sugar in the in the raw material was given as 10%. So we will multiply the 0.1, that is the decimal form, by the feed, and then equate it to the amount present in the water, which is 0. And then the water 2 is also 0. That is, there is no product in the water 2 itself, and then it is only the there is no salt in there is no sugar in the water 2 itself, and then it is only the product that contains this 50% sugar. So at the end, we are going to obtain this particular figure, that is 800 kg per h. So after getting our this particular figure, we can continue solving for the remaining variables by regarding the system to be only one evaporator. We will consider only one evaporator to get the remaining variables. So let's target the evaporator 1. So when we consider the evaporator 1 alone as a system, whatever entering evaporator 1 should be equal to whatever exiting evaporator 1. So the F is the only thing entering the evaporator 1, and it's going to be equal to W1 plus A, because A as well as W1 were exiting the evaporator 1. Although A exited the evaporator 1, but it served as the raw material for evaporator 2. So when we are considering evaporator 1 as the system, then it means that A is going to be like a product for evaporator 1. So when we fix in the values there, we are going to get 4,000 to be equal to W1 plus A as our equation 2. So we will move on and then perform component balance on sugar for the same evaporator 1. So the amount of sugar present in the feed should be equal to the amount of water, it should be equal to the amount of sugar removed from the product, as well as amount of sugar contained in the water portion. So the percentage was given to be 10%, so 0.1, and then it's going to be equal to W1 multiplying 0, since we expect the water portion to consist of only water and no other substance. And then the A, the one denoted with letter A, is also going to have a percentage of 0.18 multiplying it, that is the 0.18, which is the decimal form of the percentage, multiplying it. So we are going to get 400 to be equal to 0.18 A. So by the end, we are going to get A to be equal to 2222.22 kilogram per hour. And then we will fix this into equation 2 to solve for our A. So at the end, we are going to get A, that we are going to get W1 to be equal to 1777.78 kilogram per hour as our flow rate. The questions are not difficult, they are so simple. Just try, please, just try and then gather this particular concept. Always, whatever entering is equal to whatever exiting. If you want to get component balance, we write something like the same equation as the total balance, but here we multiply the percentage of the actual component in focus with the amount that we wrote for the total balance, and then we use it to solve the question. From equation 1, we know F to be equal to W1 plus W2 plus P. So our 4,000 is going to be equal to 1777.78 plus W2 plus 800. And at the end, we are going to get our W2 to be equal to 144.22. Thank you very much once again. Thank you very much for watching this particular video. Please don't forget to subscribe. I'm going to release another video for the remaining topics like bypass and then recycle. So please support me by subscribing to my channel. Share the link with your friends for them to also watch. Thank you very much. See you next time.